not Dan or Brian or Luke. I'm John. So before we get started, just a few administrative announcements. I will unfortunately not have office hours straight after lecture like I normally do. But I will have an extra office hour tomorrow to compensate for that. I'm really sorry for moving them around. I've been having a really hectic schedule in terms of conferences. So the office hour I was going to have today, I'll move it to tomorrow. So you'll have 2 hours of me tomorrow. And aside from that, also, I wanted to tell you guys that I know it's been a hectic week, and you've had lots of midterms and projects and homeworks due. So I just wanted you to I want to remind you of the fact that, let's see if I can get this over here. Don't forget that. Right? Don't forget that you're awesome. Okay. Woohoo! Yeah, you are. All right. Anyway, yes, because it's easy to forget that as the semester goes by. So don't forget that. So I'm not normally a PowerPoint person, so I'll be mixing this PowerPoint up with some board work as well as some group work, which is why I asked you guys to say hi to your neighbors. If you haven't said hi already, please say hi. Also, if I tend to speak a bit fast. If I speak too fast, let me know, and I'll slow down a bit. All right. All right. So bit of a tech news. I saw this online today. I thought it would be really interesting if you guys have free time this week. And also for the next 6 months, there is a display at the San Jose Museum of Art where a guy named Leo Villarreal tries to combine these LEDs into artistic shapes. So he's basically combining LEDs, the small little flashy things that you get in your remote controls and everything, and your watches. So he combines them in various patterns to produce beautiful artistic patterns. So I thought you guys might find that interesting. If you do, you can always drop by. We can even try in a field trip or something, but we'll see how that goes. All right, that's my mouse on the wrong side of the board. OK, all right. So let's get started on the actual lecture. So over the past few days, over the past few weeks, we've been talking about algorithms. And just to revise, an algorithm is basically a series of steps. I have a problem, and I want to achieve that in a certain level of steps. So I have a recipe to answer a question. So in today's lecture, we're going to talk about another big idea, which is that my PowerPoint doesn't work. There we go. Another big idea is that for every one question, there are many, many ways of doing it. So for every single question you can think of, there are a bazillion different ways of doing it. And so there are a bazillion different algorithms to accomplish that task. For instance, the very simple task of distributing candy. Right? What's the simplest way I can go around and give candy to people? Sorry? I didn't hear that. Sorry?
He said, give us money so we can help.
Oh, give us some money. I can give you some money. Yes. That's one way. Fair. That's definitely one way of getting candy out, you guys. I was thinking more along the lines of I could go to each one of you and give you candy, or I could give you money to buy candy, or I could just throw candy to you guys, and hopefully all of you will get some. Some of you might get more than one. Some of you might get less than one. But that's several different ways of doing it. And also, as we saw over the last week or so, or rather last week, we saw many different ways of looking through a list. Right? I have a list of numbers, and I want to look in that list for a specific number that I'm concerned about. I'm going to call it the 1. Right? So I'm looking in this list of numbers for the 1. So one way we can do it is what we call linear search. We walk through the list, and for each element in the list, we say, OK, are you the number that I'm looking for? If you are, then yes, awesome, I found it. If you're not, then I move to the next one. Are you the one? If you're not, move on to the next one. And we keep doing that. So we walk the list, and we try and find the number that we're looking for. Alternatively, if the list were already sorted, then we can say, oh, well, it's already sorted. So what I'm going to do is I have this huge list. Look in the middle. If that's the one that I want, awesome. If it's smaller than the one I want, then I'm going to go to the right. Otherwise, I'm going to go to the left. So that way, I keep taking the list, and I keep breaking it apart into smaller and smaller lists until I find the one that I want. Any questions up until this point? I'm sorry I don't have lecture notes out for you guys. I was going to print them out, but they copied out on me. But I'll definitely put these up online tonight. Are there any other algorithms you can think of for looking inside a list? You saw one more in lab last week. Anyone want to volunteer? Don't be scared. I don't bite. Not yet. All right, well, here's another hint. It's memoization, or actually not quite memoization. It's more the fact that what I can do at the very beginning is I can go through the list once, and I can say, oh, there's a 1 here. So inside somewhere else, I'm going to say, OK, I have a 1. So I'm going to mark. So I have a list of numbers over here, and so on. Right? So let's say I have the first 10 numbers. And I have a list of numbers, 3, 5, 6, 8, and 9. That's my list. Now I know the user is going to ask me to find numbers in this list. So I can save some effort by saying, OK, at the very beginning, before the user asks me for something, I will go through this list. And every time I see a number, I'll put a tick mark beside it. So I saw 8. I saw 3. I saw 5, 6, and 9. So that way, once the user asks me, hey, is there a 7 in this list? You can go up to your tally marks and say, oh, well, there's no 7 in that list. Sad face. How about a 6? Is there a 6? Oh, yes, there is. There's a 6 in this list. So there are several different ways of approaching the same problem. Now, the biggest question is, if we have so many different ways of approaching the same problem, what's the best way that we have? So how do we decide what algorithm to use? I have a lot of algorithms to approach the same problem. What's the best way? Which is the best one? And I have certain criteria that I can look for, like which one of them is the easier to implement. Like if this is an algorithm that's 5 lines long and there's another one that's 50 lines long, well, if I'm feeling particularly lazy, I'll go for the 5 lines one. For me, that's OK. Otherwise, I could say, OK, which of them takes less time to run? Like if I had this algorithm and another algorithm, which one is faster? Which one is slower? I'll go for the faster one, because I care about that. If I care about which algorithm uses less space, I'll say, oh, this is smaller, so I'll use this instead. And again, which gives a more precise answer? Now, this is a bit iffy, because normally we've been asking you questions like saying, what is the sum of all the lists, the sum of all the numbers in a list? We haven't asked you what is the approximate sum of all the numbers in this list. But there are some cases where you don't really want exact answers. You want a ballpark figure. Like how many people are in this room? I can do that by manually counting all of you guys. I can say, oh, well, there are 83 of you guys. But if it were Saturday and I was going to Memorial Stadium and I was like, OK, how many people are there in Memorial Stadium? Well, I can't quite go to everyone and say, oh, count, 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 count. Oh, you're going to the bathroom. OK, I'll wait for you to come back. Count, 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 count. I'll say, it's a ballpark 100,000 people. OK, that's actually too big. But I don't really care about a precise answer. I just want a ballpark figure. And also, another question is, which one of these even matters? Based on the situation I'm in, which one do I actually care about? So what I want you guys to do is to tell me what do you think is the most important in making a choice, right, using iClickers. Now, this is only an opinion poll. There is no true answer. There's no correct answer. I just want to see what you guys think. So among all the possible ways you can decide between different algorithms, do you think the ease of implementation is the most important criterion? Or how much time it takes, or how much space it uses, or which one gives a more precise answer? Or I don't really have an opinion because it's 12 o'clock and I'm sleepy. It's 12 o'clock, right? 11, sorry, yes, lunchtime. All right. So, oh yeah, so iClicker's on. Oh, cute, OK. Nice. Yep, 48 people. We're going out there. This is cool. OK. Right. By the way, there is no right answer. It depends on what situation you're in. But I want to see what you guys think. 57. How many people are in this room? Right, I think I'll do when it hits 65? 60? Right.
One more.
Woohoo! Go for 60.
Come on, 60.
Yeah, yeah. OK, so there is no 60th person. Well, that's sad. All right. So it turns out that 22 of you thought that ease of implementation is the best idea. Well, that's good. I mean, in some cases, you really care about whether or not I can get a quick and dirty prototype up running. In that case, sure, A is important. B, a lot of you guys thought B, 36%. 36 of you guys thought B, so that's awesome. C, also, some of you guys thought C, if it uses up less space, it's good for me. And only 14 of you thought that. That's actually not much of an issue nowadays, because nowadays we have so much space that we don't really know what to do with all of that. So space is less of an issue than time. But in certain cases, like in computers in your cars, for example, or in computers in your watches, you actually only have limited space. Like computers and satellites out there in space, like they have limited space. Oh, I use space in two contexts. But they have limited space, so you kind of want to ensure that your algorithm uses less space. And which gives a more precise answer? That's about 29 of you. And no one has no opinion. Cool. All right. So I'll go with the flow, and I'll say, OK, let's talk about B, which takes less time. So we're going to enter a new phase of the class, and we're going to call this runtime analysis. Ooh, fancy words, runtime analysis. Ooh. All right, what does runtime mean? So as you can tell, runtime means how long does a program take to run. So like a very commonly used criterion that we use in computer science is I have a program, and I want to see how long it takes. And how much time does it take? And how much time how much time does it take to finish its task? That's an important criteria that occurs over and over again in computer science. Because you'd rather not stay for 2 hours and look at your computer screen when you could do it in 20 minutes. 20 minutes, not hours. All right. So, OK, here's a secret. I'm going to tell you guys a secret. All right? Here's a secret. Computers are actually stupid. All right? They are as smart as, OK, this guy didn't hear it, right? OK. Computers are actually as smart as you make them. Right? They're there to do essentially what you ask them to do. Because years ago, we thought, OK, we have these problems, and we can do them for really small cases. Like I can add 2 plus 3. I can add 2 and 3. I can add 2 million and 3 million. But I can't add like huge numbers. Or I can't find the 500 digits of pi. I could do that if you gave me a lot of time. But computers do that so much faster that it's better if we ask a computer to do it for us. And that's also partially the reason why we have troubles with our computers, is because there's a bit of a difference between what we want the computer to do and what it actually does. Because what it does, it's what you told it to do, which is sometimes different from what you meant it to do. So there's a sort of a disconnect, which is why people are frustrated sometimes. But computers are actually quite stupid. So since computers are mostly useful for really large inputs, let's see how long it takes for large inputs. Let me take a script or a block or a program. Let's see how long it takes for a really large input, because that's where a computer comes into its prime. That's when a computer is awesome. How do we do that? OK. Well, what's the best way of measuring the time a program takes? Or not what's the best way? What's one instant way you can think of? Stopwatch, right? I have a stopwatch. As soon as it starts, I click it. And as soon as it ends, I see how much time it takes. Okay. Time it with a stopwatch, yay. But there are several difficulties. First off, we have a lot of different computers all over the world. Right? We have Macs, we have PCs, we have Linuxes, we have different kinds of Macs, different kinds of PCs, and sort of lots of different computers all over the world. The time it takes for them to run a specific algorithm will depend a lot on the actual computer. Right? Everyone see that? Again, the same computer itself, depending on whether or not it's morning or it's daytime or it has had coffee or it's sleepy. Computers aren't sleepy, but I've heard my computer snore. So the same computer can have different runtimes for the same input. So that gets a bit troublesome. And also, we also have to implement the algorithm if we want to run it. Right? And implementing, as you might have seen so far, is a bit of a difficulty. Because not only do you have to implement it, you have to write test cases for it. You have to debug it. It's going to fail on you. You're going to be like, why? And you have to go and trace through it. So you actually have to implement it. So wouldn't it be nice if there were a way of measuring the runtime without caring about all of these things? Right? So we have to somehow abstract the computer away from the algorithm. We have to somehow think, OK, the computer is a black box. I shouldn't care about how it is, what it is, where it is, when it is. It's a computer, and I have to separate it from the algorithm. Notice that the word abstract is in italics, because That's a word you'll see over and over again. And it's here again. Ah. All right. So runtime analysis. So how do we abstract this? How do we do this magical thing? You're probably asking, John, how do you do that? And I'd be like, OK, well, when you're doing runtime analysis, you don't actually focus on how long it takes on any one given input. Right? You take the input on which it is the worst case, and we'll see what that means in a bit. You take the worst case runtime of the algorithm, and you see how it scales as you scale the input. So you take a program, you feed it something. You take a block, you feed it something. You see how long it takes. And then you scale it a bit, and then you say, OK, now I'm going to see how long the program takes now. And I'm going to keep scaling it, and I'm going to talk about how the runtime of this algorithm scales as we scale the input. And are there any questions at this point? Please feel free to ask questions. I know it's going to be a bit too fast. There's a lot of text in there. Ah.
What do you mean by scaling?
We'll see that soon. Yeah, scaling. By scaling, I mean take the input and like perhaps multiply by 2. Or take the input, multiply by 3. We're talking about numeric inputs here. Right? So take the input, multiply by 2. Size, sorry, yes. If it's a number, what actual number it is. If it's a list, the size. So if we have a list of 4 elements and we run our program on it, let's run it for a list of 8 elements, or 16, or over 9,000. Why? Why do we do that? Well, because it abstracts the computer out. Because it separates the computer from the algorithm. Right? We can actually do runtime analysis without an actual computer. And we'll see how soon. And because the idea is, if it's a good algorithm, it'll be good no matter what computer you're on. Just like a good recipe. It's good no matter what the kitchen is or who the cook is. Which is true most of the time. If I'm the cook, then it probably will be bad. But most of the time, you want to separate the computer from the actual algorithm. OK. And why? Also because computers, as I said before, we use computers for large sets of data. Because computers are mostly useful if you have a lot of data. And computers are where they come into their prime. So you want to see that, OK, if I have a lot of data, and if I were to increase that by a factor of, let's say, 2 or 4 or a million, then the time it takes for the algorithm to scale accordingly should be reasonable. If it takes like an hour to do, if it takes like 5 minutes to do a list of a size 100, and if it suddenly takes 50 hours to do for 200 elements, then you're like, OK, that's bad. That's a bad algorithm. We want to try and improve it, make it better. Right. So the idea is basically, I'm going to take my input. I'm going to take the worst case input, see how long the script takes to run on it, or the algorithm takes to run on it, and then scale that input by a certain amount, and then check how long it takes again. And that gives us an idea as to how the runtime of this algorithm. And right. Also, a bit of a warning. How many math majors do we have in here? Do we have any math majors? All right. I'm sorry. We're going to do a lot of approximation ahead. And for some reason, that's not working. We're going to do quite a bit of approximation ahead. So we're not going to be rigorous. Right? So I'm sorry, math majors. But this is where math and computer science diverge. It's like we are engineers mostly, so we try our best to be as real world as possible. Not saying math isn't real world, but never mind. I'm not going there. Yeah. So, all right. First things first. Come on. OK, so let's talk about the basics of any algorithm. Let's talk about arithmetic operations. Let's see how long they take. Right. So I have this block here, and all it does is it adds 1 to a certain number. So you give me a number, I'll add 1 to it. Right. So demo time. OK. Yeah, you are. OK. Ignore that. Ignore. Okay. So what I have up there is I'm setting this certain number to like a large value, a largish value. Right? So let's say 10,000. And I'm going to reset what I call a timer. Now in BYOB, we have a timer. Also in Scratch, we have a timer, which is basically something that's been taken away ever since you opened this file, opened Scratch. So ever since I opened Scratch, it's been 11,834 seconds. You do the math. So what reset timer does is that it says, OK, I'm going to reset the timer, start off again, fresh. So the idea is I'm going to reset the timer, and I'm going to add 1 to this number over here. And I'm going to see how long that particular operation took. So let's try it out. So apparently, let's get a sense of how. Let's do it a lot of times. By the way, you'll be doing this in lab today. You'll be running timing experiments and see how long it'll take. But apparently, it turns out for an input which is 10,000, it takes like about 0.01 seconds. That's good. All right, let's scale it. Now, this is what I mean by scaling. Let's double it and see what happens. How long do you think? How long is it taking? Approximately the same time, 0.01. OK. That's weird. Let's double it again. Ooh. Same time. OK. Let me increase it by a factor of 10. What the? OK. Slight changes, but still 0.01. OK, I have a question for you now. If I were to add 1 more 0, how long do you think it would take? How many of us think it would be the same? How many of us think it would go up by a factor of 10? Go up by a factor of 2? All right, let's try it out. Ooh, aha, it's approximately the same. Okay. So what I did here was I took this script, and I'm saying, OK, I'm going to add 1 to this number you gave me. I'm going to progressively scale the number. And I'm going to see how long it takes. And it turns out that empirically, it turns out that it takes pretty much the same time. Does everyone see that? Within a few seconds of each other. So as the input scales, they take approximately the same time. That's the key word here, approximately. They don't change that much. And that's why they're called constant time operations. They take the same time no matter what the inputs are. Right? There's a bit of an approximation there. People in the back are probably thinking, well, that's not really true. But most cases, what we can do is, since it's an approximate analysis to begin with, we can say, OK, all of the arithmetic operations, plus, minus, star, division, and your favorite friend mod, all of them take approximately the same time, so they're constant time. And you can see that, because if I were to take a number and add 1 to it, right, I'm only ever changing the last digit. Right? So even if I make it a bit bigger, only the last digit. If I make it a bit bigger, well, it wouldn't be that, but still pretty much only 1 digit. Right? So you're only going to change the last digit. So you're always going to do the same number of operations every time. So it's a constant time operation. Questions? Yes, Henry. Right. So in this case, so what I did back there is that I took my input, which is this guy, which is 4 million. And when I say scale, I say, OK, let me scale it by a factor of 10. And let's see how the time changes. So in this case, if I change it by a factor of 10, let's say, still the same. Right? I scale the input. I multiplied it by a factor of 10. And it's still the same. Because sometimes you might expect the program to, even if you increase it by a factor of 10, you might expect its time to go up by a factor of 10. But in this case, it isn't. So you're like, what the heck? Right? But it's remaining approximately constant, which is good, because what we can do that is say that arithmetic operations take constant time. So plus, minus, star, division, mod, all constant. And notice here what Henry pointed out. I only care about how the runtime of the block scales as the input scales. So even though the actual value didn't change, like I don't actually care about the actual value. What I care about is how much it changed. And it didn't change at all. So that's another key idea we're going to explore here. OK, bit of a break. Let's do some laundry. Okay. Laundry must be done. All right. OK, so it's the weekend, and I'm doing laundry, and I'm washing my clothes. Hopefully. I don't do it very often, but I should. So now I'm like, OK, well, I'm a computer scientist. Why don't I make BYOB do it for me, right? So what I do is I make a block, launder these many loads. Right? And somehow, it probably, like, if you click on it, it reaches on a robotic arm, takes my clothes up, puts in the washing machine, and stuff happens. Right. So now my question to you is this. If each load takes approximately the same time to launder, how much time do you think, like, how does the total time or runtime scale as the number of loads doubles? So say, for example, if it takes for 3 loads, if it takes like 10 minutes, how much do you think it'll take for 6 loads? How much do you think it'll take for 9 loads? And stuff like that. So I want you guys to talk to your neighbors and see what you guys come up with. Let's see. So the question is this. I have a certain number of loads, and I say, OK, well, 3 loads takes 10 minutes. And I'm going to double it and see I'm going to see how much time that takes, or predict. OK. All right. OK, so what do you guys have for me? What happens if I double the number of loads? How do you expect the time to vary? How many of us think it'll stay the same? How many of us think it will double? How many of us think it will triple because it's cool that way? Because I'm lazy. All right, awesome. So if I were to double, so let's say it took like 10 minutes, as I said. If I were to double the number of loads that I have, then the time also should, assuming that I do them sequentially, so one after the other. If I do them sequentially, then if I do double the number of loads that I have to launder, then the time also should double as well. Right? And how about if I triple? What do you think happens? How many of us think it'll double? How many of us think it'll stay the same? How many of us think I'm not actually giving you the answer yet? OK. Yes, it will triple. Basic unitary method. So what this essentially shows is that if I scale the input by a factor of 2, then the time it takes, the total time it takes, also goes up by a factor of 2. And if I scale the input by a factor of 3, then so does the total number of time that it takes. Does everyone see that? Right? And so what we do is we call these algorithms PowerPoint failures. No. There we go. Oh, right. We call these algorithms linear time algorithms, right? Because the total time, so assuming that doing laundry is an algorithm. You go to the laundry room, put your clothes in, put your washing powder and detergent, key, coins and everything. Well, you got to go to the bank first and get coins. But the total time it takes for this algorithm scales by the same amount. If I double the load size, I also double the time it takes. So doing laundry is what I call a linear time operation. And the reason we call it linear is because if I were to draw a plot of this, with like loads and time, I would expect a sort of a line graph. Any questions? OK, let's try something else. What if I'm done my laundry's dried, and now I want to find clothes to wear? Yes. So I want to find clothes to wear for today's lecture. And I already have them, so thankfully I'm clothed. But the question is this. Now I have a block that does this for me as well. I have a certain number of shirts and pants. Let's say I have 6 shirts and 6 pants. Now I want to find a good pair to wear. And the way I'm going to do this is I'm going to say, OK, I'll take the first shirt, and I'll take the first pant, and I'll see if it looks good. If not, I'll take the first shirt and the second pant, the first shirt and the third pant, the first shirt fourth, first shirt fifth, first shirt sixth. And I'm like, oh, they don't match at all. The first shirt sucks. So I go to the second shirt. And I keep doing that, right, until I finally find a good pair. Right? And so what's the worst case scenario in this case? Like, what's the longest time I can take on this thing? Like, in what situation would I take the longest time? Right, if the pair's at the very end, right? If the last shirt and the last pant that I see are actually the one that I care about, that they look good. So this is actually an iClicker question. So I'm going to ask you guys to talk to your neighbors and see what happens. How does the worst case total time to find a good pair scale as the number of shirts and pants doubles? So what I mean by that is, let's draw a similar thing here. Where are they? OK. So let's say I have the same number of shirts and pants, and they're all different. So let's say for 3 shirts and 3 pants, I take some amount of time. Worst case. Now I want you to tell me, how do you think this time will scale as you double the number of shirts and pants you're giving me? So does it stay the same? Does it double as well? So if I double the shirts and pants that I have, does the total time also double? Or does it half? Or does it quadruple? Or you're like, what? And there's a hint. For each shirt that I own, how many pants do I have to match against it? Right. So for each shirt that I own, how many pants do I have to match? And therefore, since for each shirt, what's the total for all the shirts? So does this question make sense? So in this case, the worst case was if the shirt and the pant that I actually care about is at the very end. So now I want to see how the total time it takes scales. So if you double the number of shirts and pants you gives me, how does the total time also scale? So talk with your neighbors, see what you guys come up with, and we'll come back in like 3 minutes. Yes, use iClicker. Oh, by the way, yeah, use your iClicker. Once you have an answer, once you agree on an answer, click on the iClicker. See how that goes. Only change what?
It's only changing.
Oh, right. Oh. This was the simplest thing I could come up with.
Calculation time is dominated by the instruction factor.
There. Oh, yeah. Should I correct that? Oh. Yeah, okay. I think I'll keep it there. It's actually, I'll think, because that's actually, yes. Oh, man. All right. Okay. All right. Ooh, you guys have, all right, 55. We're reaching, so it was 59 last time, so 4 people haven't voted yet. But an overwhelming of you think it quadruples. And 5% of you think, what? Okay. We'll fix that. But none of you think that it doubles, which is real. Oh, 2 of you think that it doubles. Never mind. 2%. Okay. All right. And I'll go with the majority. Yes, it actually does quadruple. So let's actually see why. Come on, give me some love. Okay, so let's take an example, right? Let's take, I have 3 shirts and 3 pants. If I have 3 shirts and 3 pants, there are 9 different things I have to check, right? Because I can take the first shirt and I have 3 pants against it. The second shirt, I also have 3 pants against it. The third shirt, I have 3 pants against it. And they're distinct shirts, right? I mean, they could be the same shirt, but then the problem isn't that fun. So I have 9 possible combinations, right? Now, let's double it. If I have 6 shirts and 6 pants, then for each shirt, I have 6. So now 6 times 6 is 36. So I double the number of shirts and pants, but notice that even if I double the number of shirts and pants that I have, then the number of different combinations that I can try, and therefore the total number of time that I take, quadruples. Right? Assuming that it takes me the same amount of time to try on a shirt and a pant. Right? Bear in mind, this is all approximate. So I mean, I could take a while to put on a suit pant, and I could take less time to put slacks on. But I'm saying, assume they take the same time to try on, and assume that I double it. What happens to the total number of time it takes? And as you notice, if you double the number of shirts and pants, you quadruple the time it takes. Right? So we call these algorithms. So the runtime of the algorithm scales by the square of the amount that is scaled by. So last time, here we scaled the number of shirts and pants by 2. So the total number of times scaled by a factor of 4. So we call these things quadratic time algorithms because there's a square involved. So you'll be seeing this in lab today, all these different kinds of algorithms, and you're going to be playing with them quite a bit. You're going to be timing them and see how they play with actual time. But notice that in all of these cases, we didn't actually talk about the precise number of time that I took. Right? Here I gave an example to solidify it, but it could be any number of time, right? Any proper time amount. What we cared about was how much it scaled, how much change happened as you went from one to the other. All right, so laundry's been done. Yay. OK. So any questions until this point? All right, we have about 10 minutes. Oh, also, just wanted to clarify. When you say something about how much time it takes, you also say what in. In this case, since my input is a number of shirts and pants, I would say, to be more rigorous or precise, it's quadratic time in the number of shirts and pants. You don't have to worry about that too much, but it's an interesting fact. All right, so let's try our hand. Let's try our hand at stuff. I have a script here. It sets num to 0, and it does that loop num times. It changes num by 1. It's a very simple loop that just adds 1 num times. What is the runtime of the script? It's again, it's again an iClicker question. So is it constant in num? Is it linear in num? So is it a constant time algorithm? Is it a linear time algorithm? Is it a quadratic time algorithm? What? And there's no 5. I mean, there could be a 5, but there is no 5, so never mind. you do click a 5, and I'll take it as a sign that you're sleeping. So does everyone understand the question? I have this algorithm. I set something to 0, and I have this loop that changes num by 1 each time. Now I want to see what is the runtime. Like, what category does it fit in? Is it a constant time algorithm? Is it a linear time algorithm? Is it a quadratic time algorithm? All right. Ooh, that's cool. Okay. Yes? Hi, question. Oh, 4? Oh. Yeah. Aw. Right. Okay. Ooh, I think we've reached steady state. Okay. So you guys are equally split between constant time and linear time. Some of you think quadratic, and at least one of you thinks both. Okay, so let's actually look at the loop. Right? So the loop says, OK, I'm setting this num to 0, and I'm going to repeat this loop num times. Right? So if I set num to 3, how many times does a loop run? How many times? Yeah, 3.
0.
Ah, right. No, yes. Dang it. OK. Brian, this is a fair point. OK, so assume that 3 was plugged into that. Instead of 0, you had 3 in there. Yes. Was that confusing? I'm sorry.
Yes.
OK. Yes. 3 goes into 0, where 0 was. Does that mean we revote?
Yes.
OK, let's revote. So yeah, sorry. In this case, think of replacing 0 by 3. And how many times does the loop run? Actually, in this case, if you kept it like this, yes, it would be constant. It wouldn't run at all. But yeah. Oh, yeah, so assume like, OK, ignore the set num to 0 bit, basically. I wonder if I can do that. OK, let's see. Insert, design, insert, shapes, that. OK, so yeah, basically ignore that little thing there. Yes. Yeah. OK, so all right, awesome. So that's an overwhelming majority for linear num. Yes, awesome. So if you were to ignore that set block, I'm sorry about that, you notice that if num were, for example, 3, the loop runs 3 times. If it were 6, it runs 6. For 9, it runs 9. So notice that if I scale the input, I scale the number of times the loop runs, and therefore approximately the total number of time it takes by the same factor. Question at the back. OK. All right, let's go for another one. And I am going to resume slideshow. OK. Again, ignore the set num to 0, although this doesn't quite matter. What is the runtime of this script? Question?
I had a question about the last slide.
Yeah? Oh.
How does, like, what's in the C block affect how many times it runs? Doesn't it?
Right. So in a repeat block, You only determine how many times you want to run it the very first time, right? Not as you change it. And that's a very good question. Here you notice you're changing num by 1 as you're going inside the repeat block. So you're probably thinking, OK, well, that means the first time I'll repeat it 3 times, the next time I'll repeat it 4, next time I'll repeat it 5. That's actually a very good interpretation. But what Scratch does is it saves you from yourself. And it says, OK, I'm going to save that number the very first time you send it to me. So let's try the next one. All right. Ooh, you guys are killing this. All right. 3 minutes. All right. We're going to kill this soon. All right. Any questions about this so far? Yeah. Is the input? No, the input in this case. So notice I say a constant in num. So in this case, the input is num. All right. OK, so what do you guys think? You guys are overwhelmingly thinking that is constant in num. Exactly, it's constant in num because no matter what the value of num is, that loop will always repeat 10 times. Right? That loop is distinct from the actual value of num. It'll always run 10 times. Right? So it's approximately constant time. So you guys are awesome. It will run constant in num. Let's end this with a little bit of a harder question. OK. Again, ignore that set num to 0 block. All right, how about this guy? Is he constant? Is he linear? Is he quadratic? Is he something I haven't told you yet? OK, wow, you guys are killing this. Ignore the set num to 0, yeah. Assume that by this point you already have it, yeah. All right. OK, and you guys are overwhelmingly thinking, yes, it is quadratic. Right? Because for any specific value of num, that loop right there repeats num square times. Because for each possible iteration of the outer loop, the inner one runs num times. It's like the shirt and pants thing. You can think of the outermost one as the shirts, and the innermost one as the pants. So it's shirt and pant. So it is quadratic. And there's a minute left. Can I risk a question?
Yeah.
OK, let's see. Let's try this last question. What if I said num minus 1? Is it constant, linear, quadratic, or both? All right, you guys are kind of like moving on to a smoother graph here. Yeah, so I'll go with the flow. It is actually quadratic. So that's a bit weird because you have num and num minus 1 at the inside. So technically speaking, it's num squared minus num, right? But remember what I said at the very beginning of this lecture was we only care about really, really large values of num. So notice that let's say my input size is like 10, 100. So I'm scaling it by 10 each time. Notice that if it were a linear program, it's also going to scale by the same amount each time, right? But if it's a quadratic, it's going to scale by square of that. So eventually, it's going to get so huge that it's going to eclipse, not the movie, it's going to eclipse the linear part, right? So you have n squared minus n. But for really, really, really large values of n squared minus n is somewhat n squared. So, yeah. All right, thank you guys for a great lecture. I'll see you guys in lab.